Hello there, and welcome again to the Dozing Explorer. I'm so glad you've chosen to join me tonight for this quiet exploration. Find a place where you can rest completely, letting your body settle heavily into comfort. There is nothing expected of you here, no task to complete. Simply allow yourself this time for stillness. My voice will be your companion as we drift into the largest scale structures in the cosmos. Tonight, our journey takes us into the immense and silent realms known as cosmic voids. We won't be navigating complex astronomical charts, but rather floating through these vast expanses of near emptiness as a pathway toward deep relaxation. We will contemplate these regions not as mere gaps, but as fundamental components of the universe's structure, places of profound calm that define the luminous patterns of the cosmos. This is an exploration of absence, of stillness, on an unimaginable scale. We will imagine the universe as a delicate, luminous web and explore the vast, dark spaces that give this web its form. We'll consider the few lonely galaxies that drift within these great expanses and the ancient light that travels unimpeded across them for billions of years. This is a story about the beauty of sparseness, the tranquility of isolation, and the serene architecture of the universe revealed in its grandest, quietest spaces. And just before we embark, if you find that these explorations help you unwind and find sanctuary for your mind, perhaps consider liking and subscribing. It's a simple gesture that helps others seeking tranquility find their way here, and it allows our journeys together to continue. But for now, release that thought. Your only focus is your own comfort, your own ease. Breathe slowly and deeply. Grant your mind permission to wander among these ideas, or to simply let go entirely, drifting into sleep whenever it feels natural. Let the vastness embrace you. Let the journey begin. There are vast spaces in the universe that are almost completely empty. While we often focus on the bright stars and galaxies, the grand structure of the cosmos is largely defined by immense regions containing very little matter. These are the cosmic voids, enormous volumes, where the density of galaxies falls far below the universal average. They are not absolute vacuums, but compared to the dense filaments and clusters where galaxies congregate, they are realms of extraordinary sparseness, great hollows in the fabric of space-time. The universe, it turns out, is mostly composed of these enormous under-occupied spaces. These are the cosmic voids, the largest structures in the cosmos. When astronomers map the distribution of galaxies on the grandest scales, they find that galaxies are not spread uniformly but are arranged in a vast network often called the cosmic web. The voids are the immense, bubble-like regions that fill the space between the bright filaments and walls of this web. Individual voids can span hundreds of millions of light-years, dwarfing even the largest superclusters of galaxies, making them the most voluminous structures known. They are the great, defining spaces of the universe's large-scale architecture. A void can be hundreds of millions of light-years across. The sheer scale of these structures challenges comprehension. Our own Milky Way galaxy is about 100,000 light-years wide. A typical cosmic void could contain thousands of Milky Ways lined up end-to-end across its diameter. Light itself, the fastest thing in the universe, takes hundreds of millions of years simply to cross from one side of a large void to the other. They represent distances that belong more to the realm of cosmic history than everyday experience. They contain far fewer galaxies than expected. If galaxies were distributed randomly throughout space, a region the size of a cosmic void would be expected to contain tens of thousands of them. Instead, astronomers typically find only a handful, or sometimes none at all, within these vast volumes. Their defining characteristic is this profound lack of luminous matter, this deviation from the cosmic average density. They are defined by what they lack: vast arenas mostly devoid of stellar cities. Imagine a room the size of a continent with only a few grains of sand inside. This analogy helps to grasp the extraordinary emptiness of a cosmic void. Compared to the density of matter within galaxies, or even within the filaments of the cosmic web, the voids are incredibly rarefied. The few galaxies that do reside within them are separated by truly immense distances, like solitary grains of sand lost in an unimaginably vast and otherwise empty chamber. It is sparseness taken to a cosmic extreme. Cosmic voids make up the vast majority of the universe's volume, while the bright filaments and clusters of the cosmic web contain most of the universe's mass and nearly all its visible light. They occupy only a small fraction of its total space. The immense voids that fill the gaps between these structures constitute perhaps 80 to 90% of the volume of the observable universe. Most of the cosmos is actually these great dark and quiet expanses. Emptiness is the rule. Structure is the exception. They are the quiet, dark spaces between the bright filaments of galaxies. The cosmic web is often visualized as a luminous network against a dark background. The voids are that background. They are the deep, serene darkness that allows the structure of the filaments and clusters to stand out in such beautiful contrast. Without the voids, the universe would be a uniform, featureless expanse. The emptiness is what gives the cosmos its intricate and captivating form. The darkness shapes the light. The universe is structured like a sponge, and voids are the empty holes. This is another useful analogy for the large-scale structure. Imagine a sponge with its interconnected walls and the large empty spaces within. The walls of the sponge represent the filaments and sheets where galaxies cluster, and the holes represent the cosmic voids. This sponge-like topology with vast interconnected regions of emptiness seems to be the fundamental geometric pattern of the cosmos on its grandest scale. Reality possesses a porous, intricate architecture. These spaces are profoundly silent and still. Within a cosmic void, the environment is one of almost perfect tranquility, far from the gravitational jostling and energetic events common in dense galaxy clusters. The voids are places of deep calm. The few particles that exist there drift slowly through space with little interaction. There are no shock waves from supernovae, no powerful jets from active black holes. It is the universe in a state of deep, undisturbed meditation. The light from distant galaxies travels through these voids to reach us. The photons arriving at our telescopes from the farthest reaches of the universe have spent much of their multi-billion-year journey traversing these immense cosmic voids. The emptiness of the voids allows this ancient light to travel almost entirely unimpeded, preserving the information it carries about the distant objects that emitted it. They are the clear, transparent highways for cosmic information. They are not perfectly empty, but contain a whisper-thin gas. While devoid of large structures like galaxies, cosmic voids are not absolute vacuums in the strictest sense. They are permeated by an incredibly tenuous diffuse gas, primarily hydrogen and helium left over from the Big Bang. This intergalactic medium within the voids is far less dense than in the filaments, perhaps only a few atoms per cubic meter, but it represents a significant portion of the universe's total normal matter. It is an almost imperceptible cosmic atmosphere. This gas is colder and less dense than anywhere else in the cosmos. The gas residing within the cosmic voids exists in a state close to the universe's primordial condition. It has not been significantly heated by star formation or galactic activity, nor has it been compressed by gravity. It remains incredibly sparse and profoundly cold, only slightly warmer than the absolute zero temperature set by the faint afterglow of the Big Bang itself. It is the universe's undisturbed primordial air. Voids are places of deep cosmic peace. Their defining characteristics: immense scale, profound emptiness, extreme cold, lack of energetic events, and pervasive silence combine to make cosmic voids the most tranquil environments in the entire universe. They represent a baseline state, the quiet backdrop against which the more dynamic processes of cosmic evolution unfold within the denser regions. They embody stillness on a scale beyond imagining. They have existed since the early universe began to form structure. Voids are not recent phenomena, they are ancient features of the cosmic landscape. They began as tiny regions in the primordial density field that was slightly less dense than average. Over billions of years, gravity amplified these initial slight deficits, pulling matter away from the underdense regions and towards the overdense ones. Voids grew concurrently with the filaments and clusters, their emptiness carved out by the very process that built the luminous structures. They are the negative image of cosmic assembly. These filaments might host a few small, isolated galaxies. The rare galaxies found within voids might preferentially reside along these faint, internal filaments. These galaxies would represent the most isolated populations in the universe, evolving in an environment almost entirely free from external gravitational influences or interactions with other galaxies. They are inhabitants of the universe's most remote cosmic byways. The structure of voids helps us understand dark energy's gentle push. Because voids are regions where the effects of gravity are minimized, they are ideal places to study the influence of dark energy. The rate at which voids grow and the subtle effects they have on light passing through them, like the ISW effect, provide crucial observational constraints on the nature of this mysterious force that is accelerating the expansion of the universe. Emptiness magnifies the universe's subtle acceleration. While mostly empty, voids are not entirely devoid of galaxies. Observations have confirmed the existence of galaxies residing deep within the cosmic voids, far from the bright filaments and clusters. These void galaxies are rare compared to their counterparts in denser regions, but their presence demonstrates that galaxy formation can occur, albeit less efficiently, even in the most underdense environments in the cosmos. Life finds a way, even in the cosmic deserts. A few rare galaxies can be found drifting within these vast spaces. These galaxies are true cosmic hermits, living lives of profound isolation. Their nearest neighbors might be tens or even hundreds of millions of light-years away, across vast gulfs of near-perfect emptiness. Their existence within the voids is a testament to the fact that the initial seeds of structure formation were present everywhere, even in regions that would later become predominantly empty. These void galaxies are often small, blue, and actively forming stars. Compared to galaxies found in dense clusters, which are often large, red, and quiescent, void galaxies tend to be smaller, less massive, and bluer in color. The blue color indicates ongoing star formation. Living in isolation, they have likely retained their primordial gas reservoirs and have not experienced the environmental effects, like gas stripping or frequent mergers, that tend to shut down star formation in denser regions. Isolation preserves their youthful activity. They live in profound isolation, millions of light-years from their nearest neighbor. The separation between galaxies within a void is immense. Imagine the Milky Way and Andromeda, currently about 2.5 million light-years apart and destined to merge. A typical void galaxy might have no comparable neighbor within 50 or 100 million light-years. This isolation shapes their entire evolutionary history, protecting them from external disturbances. They are islands of light in an ocean of darkness. If our Milky Way were inside a void, we wouldn't have known other galaxies existed until recently. The vast distances mean that even large galaxies like Andromeda would appear incredibly faint and small if viewed from the center of a void. It likely would have required the development of large telescopes in the 20th century to even detect their existence. For most of history, inhabitants of a void galaxy would understandably believe their own stellar island was the entirety of the universe. Emptiness conceals the existence of neighbors. The night sky in a void galaxy would be incredibly dark and sparse. From a planet within a void galaxy, the night sky would look vastly different from our own. While the stars of the home galaxy would be visible, the surrounding intergalactic space would appear almost completely black. There would be no nearby Andromeda to observe, No rich Virgo cluster filling the view, just a profound and almost featureless darkness, dotted with perhaps a few incredibly faint, distant smudges reachable only by powerful instruments. It would be a sky emphasizing solitude. These galaxies likely formed from the small amount of matter that remained in the void. While most matter flowed out of the void regions, some small fluctuations likely remained or collapsed later. These provided the seeds for the formation of the few galaxies we find there today. They represent the less successful outcomes of structure formation, the smaller seeds that grew in less fertile ground compared to their cousins in the dense filaments. They are survivors in a sparse land. They evolve differently than galaxies in dense clusters. Galaxies in clusters are constantly interacting with each other and with the hot intracluster gas. These interactions can trigger bursts of star formation, strip away gas, or lead to mergers. Void galaxies living in isolation evolve much more peacefully. Their evolution is primarily driven by their own internal processes, making them cleaner examples of how galaxies might form and change without significant environmental disturbance. Isolation fosters a simpler life story. They experience fewer mergers and interactions with other galaxies. The immense distances between void galaxies mean that collisions and gravitational encounters are extremely rare events in their history. Unlike galaxies in clusters, which might undergo multiple mergers over their lifetimes, void galaxies tend to grow slowly and quiescently through internal star formation, largely undisturbed by their neighbors. Their history is one of quiet self-sufficiency. This makes them pristine laboratories for studying galaxy formation in isolation. Because their evolution is less complicated by environmental factors, void galaxies offer a unique opportunity to test theories of galaxy formation and evolution in their simplest form. They allow astronomers to isolate the effects of internal processes like feedback from star formation and supernovae without the confusing influence of frequent mergers or gas stripping. They are controls in the grand cosmic experiment. Void galaxies often have a purer, more primordial gas composition. Having experienced fewer generations of star formation and less mixing with material ejected from other galaxies, the gas within void galaxies is often less enriched with heavy elements compared to galaxies in denser environments. They retain a chemical composition closer to that of the early universe, providing valuable clues about the primordial state of galactic building blocks. They hold a clearer memory of the universe's chemical beginnings. They are like quiet, small towns in the vast rural expanses of the cosmos. If galaxy clusters are the bustling metropolises of the universe and filaments are the connecting highways and suburbs, then void galaxies are the isolated, small towns situated deep in the quiet countryside. They lead a slower, more self-contained existence, far from the influences and interactions of the cosmic urban centers. Their existence shows that life can find a way even in the universe's quietest corners. While the conditions for complex life as we know it might be less common in the smaller, less chemically enriched void galaxies, their mere existence demonstrates the pervasive nature of structure formation. Even in the most underdense regions, gravity was able to gather enough material to initiate the processes of star birth and galaxy assembly. Structure finds purchase even in the sparsest soil. Some void galaxies are connected by faint, thin bridges of gas. Detailed observations have occasionally revealed extremely faint filaments of hydrogen gas stretching across voids, sometimes linking isolated dwarf galaxies. These tenuous bridges might represent the last vestiges of the cosmic web structure within the void, potentially serving as pathways for gas accretion or future interactions, albeit on incredibly slow timescales. Even the emptiness has subtle connecting threads. Light from the Big Bang, the cosmic microwave background, travels through the voids. The faint, uniform afterglow of the Big Bang permeates the entire universe, including the vast cosmic voids. This ancient light began its journey almost 13.8 billion years ago and has been traveling through expanding space ever since. Its path carries it unimpeded across the immense emptiness of the voids before reaching our telescopes. Voids are transparent windows onto the universe's earliest light. As this light passes through a void, it is subtly affected by the expansion. The journey of CMB photons through a void is not entirely without effect. As a photon enters the void's slightly weaker gravitational field, it gains a tiny amount of energy, blue shift. As it climbs back out, it loses energy, redshift. Because the universe continues to expand while the photon is inside, the void becomes slightly larger and shallower, meaning the photon regains slightly less energy on its way out than it gained on its way in. This results in a net energy loss, appearing as a slight cooling. The stretching universe leaves a subtle chill on light crossing its emptiest spaces. This effect, called the integrated Sachs-Wolf effect, can create cold spots on the CMB map. If a particularly large supervoid lies along our line of sight, this subtle energy loss experienced by CMB photons passing through it can create a detectable cold spot in the otherwise remarkably uniform temperature map of the early universe. This ISW effect is a powerful, though challenging to measure, probe connecting the largest structures in the late universe, voids, to the pattern of light from the very beginning. The largest empty spaces cast faint, cool shadows on the light of creation. Thinking about voids offers a perspective on immense scale and quietude. Contemplating these vast expanses of near-nothingness can provide a profound sense of perspective. Our own existence, teeming with activity on a small planet within a bustling galaxy, is set against this backdrop of immense, silent emptiness. Voids remind us of the universe's dominant state, vast, dark, and still, making the luminous structures we inhabit seem even more precious and remarkable. Their emptiness highlights the richness of our own small corner. Voids grew from tiny regions of slightly lower density in the early universe. The seeds of the cosmic voids were present in the almost perfectly smooth state of the universe shortly after the Big Bang. Tiny quantum fluctuations created minuscule variations in density from place to place. Regions that happened to start out with slightly less matter than average became the gravitational lowlands. As the universe expanded, these initial small deficits grew dramatically over time. The largest structures originated from the smallest imperfections. Gravity pulled matter away from these regions, making them emptier over time. Gravity acts to amplify density contrasts. Matter is pulled towards regions that are already denser, and consequently it flows away from regions that are less dense. This gravitational evacuation is the primary mechanism for void formation. Over billions of years, the subtle initial density deficits were transformed into vast regions almost completely devoid of matter as gravity relentlessly sorted the cosmic material. Gravity sculpted emptiness as much as it built structure. The matter flowed towards the denser regions that became filaments and clusters. The material that evacuated the voids did not disappear. It accumulated in the regions that started out slightly denser than average. These regions grew into the vast, interconnected network of filaments, sheets, and dense clusters that form the cosmic web. The formation of voids and the formation of the luminous structures are two sides of the same coin, a single, grand process of gravitational reorganization. Structure emerges as emptiness deepens. Voids are a natural consequence of gravity sculpting the cosmos. They are not exotic or mysterious objects, but an inevitable outcome of how gravity operates on large scales over cosmic time, starting from small initial density fluctuations. In any such system, regions will naturally become denser, while others become more rarefied. Voids represent the extreme end of this natural sorting process, the logical counterpart to the formation of galaxies and clusters. They are the valleys created as gravity builds mountains. They are shaped by the surrounding filaments and walls of galaxies. Voids do not typically have simple, perfectly spherical shapes. Their boundaries are defined by the complex web-like arrangement of the galaxy filaments and walls that surround them. They fill the irregular spaces within this network, often taking on complex, interconnected, or elongated forms. Their shape is a negative imprint of the luminous structure around them. They are defined by the contours of their luminous neighbors. Some voids are roughly spherical, while others are more irregular. While the underlying physics might favor spherical expansion in idealized scenarios, the messy reality of the cosmic web structure means that voids come in a variety of shapes and sizes. Some smaller voids embedded within denser regions might be nearly spherical, while the largest voids, spanning the gaps between major superclusters, often have more complex and amorphous boundaries. Their geometry reflects the complexity of the cosmic tapestry. The boundaries of voids are not sharp walls, but gentle, gradual transitions. Unlike the edge of a bubble in water, the edge of a cosmic void is not a distinct surface. The density of galaxies typically decreases smoothly and gradually as one moves from a filament into a void. There is no clear line marking where the void begins, but rather a slow fading out of structure over millions of light years. It is a soft and fuzzy boundary, a slow descent into profound emptiness. They are defined by the absence of large structures. The primary definition of a void is observational. It is a region where surveys find significantly fewer galaxies, especially bright, massive ones, compared to the cosmic average. While they contain some matter, they lack the characteristic large-scale structures, galaxy groups, clusters, and dense filaments that dominate the rest of the universe's volume. Their identity lies in their lack of cosmic landmarks. Dark matter, like normal matter, is scarce within the voids. Just as galaxies are rare in voids, the invisible dark matter that forms the universe's underlying scaffolding is also significantly depleted in these regions. Dark matter, being subject to gravity, also flowed out of the underdense regions and accumulated in the filaments and clusters. Voids are regions where both the luminous and the dark components of the universe are profoundly sparse. Emptiness applies to both the seen and the unseen matter. The gravitational landscape inside a void is incredibly flat and calm. Because there is so little mass within a void, the curvature of space-time there is minimal. The gravitational potential is very shallow compared to the deep wells created by galaxy clusters or the gentle slopes along filaments. This means that any object inside a void experiences very weak external gravitational forces, leading to slow, undisturbed motion. It is a place of profound gravitational tranquility. Voids are like vast, slow-moving bubbles expanding within the cosmic web. As the universe expands, the voids expand along with it. In fact, because they have less internal gravity to resist the expansion, they tend to grow slightly faster than the denser regions. Over cosmic time, the voids effectively push the filaments and clusters farther apart, acting like rising bubbles that shape the overall structure of the cosmic foam. Their expansion drives the evolution of the web. The expansion of the universe happens slightly faster inside a void. The rate at which space expands, the Hubble constant, is influenced locally by the density of matter. Inside a large void where the matter density is much lower than average, the decelerating pull of gravity is weaker. Consequently, the universal expansion driven by dark energy proceeds at a slightly accelerated rate compared to denser regions like galaxy clusters. Emptiness allows space-time to stretch more freely. This is because there is less matter and gravity to counteract the expansion. The cosmic expansion initiated by the Big Bang is in a constant tug-of-war with the mutual gravitational attraction of all the matter in the universe. Where matter is dense, gravity acts as a stronger brake on the expansion. In the voids, this brake is almost non-existent, allowing the underlying expansion of space-time, potentially accelerated by dark energy, to proceed almost unimpeded. Gravity's grip is weakest in the empty spaces. Voids grow larger over cosmic time as the universe expands. As space itself stretches, the voids naturally stretch along with it, becoming more voluminous. Additionally, the continued gravitational evacuation of matter from their interiors and the slightly faster expansion within them contribute to their growth relative to the denser structures. Voids are becoming increasingly dominant features of the cosmic landscape as the universe ages. The emptiness is slowly taking over. They are becoming an increasingly dominant feature of the cosmic landscape. In the far distant future, assuming the accelerated expansion driven by dark energy continues, the voids will grow so large that they will effectively isolate the remaining galaxy clusters and superclusters from each other. These structures will become causally disconnected islands in an overwhelmingly vast ocean of emptiness. The future universe may be one dominated by profound cosmic isolation. The final state might be mostly void. The largest known void is potentially linked to the CMB cold spot. In the map of the cosmic microwave background, CMB radiation, there is an unusually large and cold region known as the cold spot. One possible explanation for this anomaly is the presence of an enormous supervoid along the line of sight, perhaps billions of light-years across. Light traveling through such a vast underdensity could lose slightly more energy than expected via the integrated Sachs-Wolf effect, resulting in the observed cold patch. This connects the largest structures to the earliest light. It is an unusually large and empty region, potentially billions of light-years across. While typical large voids measure a few 100 million light-years, the Eridanus supervoid proposed to explain the cold spot would be significantly larger, potentially representing one of the most extreme underdensities in the entire observable universe. Its sheer scale challenges some cosmological models and highlights the potential for unexpected structures within the cosmic web. It represents emptiness on an almost unbelievable scale. Some voids contain faint, wispy filaments of dark matter crossing through them. While dominated by emptiness, simulations suggest that voids are not entirely featureless. Faint extensions of the larger cosmic web filaments, composed primarily of dark matter, might thread their way across these vast expanses. These wispy tendrils would represent the last vestiges of structure within the void, potentially hosting a few small, isolated dwarf galaxies. Even the emptiness contains subtle threads. Voids act as gentle lenses, subtly distorting the images of galaxies behind them. Just as massive clusters can act as strong gravitational lenses, the immense underdensities of voids also affect the path of light, but in the opposite way. Voids act as weak, diverging lenses, slightly demagnifying and distorting the shapes of galaxies seen through them. This weak gravitational lensing effect is statistically measurable over large areas of the sky. Emptiness subtly reshapes the appearance of the light passing through. This weak lensing allows us to map the distribution of mass. By measuring the subtle, coherent distortions in the shapes of millions of background galaxies, astronomers can reconstruct the intervening distribution of all matter, both luminous and dark. Voids show up in these mass maps as regions where the lensing signal indicates a significant lack of matter, complementing the positive signals seen from clusters and filaments. We can map the emptiness by its subtle effect on background light. Voids leave a faint, negative imprint on maps of cosmic structure. Whether mapping the distribution of galaxies directly or inferring the distribution of mass through lensing, voids appear as the great underdense regions that define the cosmic web. Their presence and properties are a crucial component of our understanding of large-scale structure, providing information complementary to that gleaned from studying the dense regions. The cosmic tapestry is defined as much by its holes as by its threads. High-energy cosmic rays travel unimpeded through the vast emptiness of voids. These energetic particles, accelerated in events like supernovae or near black holes, travel across the universe at nearly the speed of light. When their paths take them through cosmic voids, they encounter virtually no matter or magnetic fields to interact with or deflect them. Voids are essentially free travel zones for the universe's most energetic messengers. The empty spaces offer clear highways for the fastest particles. Neutrinos, ghostly particles, stream silently through voids without interaction. These fundamental particles interact extremely weakly with matter. Billions of neutrinos from the Sun and other cosmic sources pass through our bodies every second without effect. They travel across the vast intergalactic distances, including the immense voids, almost completely oblivious to the sparse matter that resides there. Voids are utterly transparent to these elusive cosmic phantoms. Even the faintest gas poses no obstacle to the neutrino's journey. Voids are transparent windows allowing us to see the most distant universe. Because they contain so little gas and dust compared to galactic disks or dense clusters, voids offer exceptionally clear lines of sight across cosmological distances. They do not significantly absorb or scatter the light from background objects, making them ideal regions to search for the faintest and most distant galaxies and quasars. Their emptiness provides unobscured views of cosmic dawn. They contain very little dust to obscure the light from faraway objects. Cosmic dust, composed of tiny grains of heavier elements, is primarily produced within galaxies. Since galaxies are rare in voids, these regions are largely free of the obscuring dust that often plagues observations within or behind galactic structures. This lack of dust contributes to their transparency, particularly at shorter wavelengths of light. The cosmic air is clearest in the empty spaces. The emptiness of voids preserves the purity of signals traveling through them. Light and other signals traversing voids are minimally affected by absorption, scattering, or gravitational lensing compared to paths through denser regions. This means that the information encoded in these signals, e.g., the spectrum of a distant quasar, arrives at Earth in a relatively pristine state, allowing for clearer interpretation of the source's properties and the intervening medium. Emptiness acts as a near-perfect transmission medium. Studying light that has passed through voids tells us about their subtle properties. While mostly empty, voids are not entirely featureless. By carefully analyzing the faint absorption lines in quasar spectra caused by the tenuous gas within voids, or by studying the subtle weak lensing effects, astronomers can measure the residual density, temperature, and even potentially the weak magnetic fields within these vast regions. The emptiness itself holds subtle clues. They are serene laboratories for testing fundamental physics over vast scales. Because voids are regions where complex astrophysical processes like star formation and feedback are minimal, they provide a clean environment to test fundamental physics, such as the nature of dark energy or potential modifications to gravity. The behavior of light and the subtle motions of the few galaxies within voids can offer unique constraints on these deep cosmological questions. Simplicity allows for clearer tests of fundamental rules. Even in a void, space itself has properties and energy. According to modern physics, the vacuum is not truly empty but possesses a ground state energy, often associated with dark energy. This vacuum energy is present everywhere, including within the voids, and its repulsive gravitational effect is thought to be the driving force behind the universe's accelerated expansion. Even the emptiest space possesses an intrinsic, subtle energy. Dark energy's effects are most apparent in the voids, where gravity is weak. In dense regions like galaxy clusters, the attractive force of gravity overwhelms the gentle, repulsive push of dark energy. However, in the vast, underdense voids, gravity is very weak, allowing the subtle effect of dark energy to dominate the dynamics. The slightly accelerated expansion within voids is a direct manifestation of dark energy's influence on space-time itself. Emptiness reveals the universe's underlying expansive tendency. Quantum mechanics suggests even empty space is filled with virtual particles flickering in and out. At the quantum level, the vacuum is a seething cauldron of activity. Pairs of virtual particles and antiparticles constantly pop into existence, borrowing energy from the vacuum for a fleeting moment allowed by the uncertainty principle, before annihilating each other and disappearing again. This quantum foam underlies all of space, including the cosmic voids. Absolute nothingness may not truly exist. The vacuum hums with fleeting potential existence. Voids are not absolute nothingness, but the closest the universe comes to it. While containing trace amounts of gas, dark matter, faint magnetic fields, and quantum fluctuations, cosmic voids represent the lowest density environments achievable on large scales within our universe. They are the ultimate expression of sparseness, the serene baseline against which all cosmic structures are measured. They embody the profound emptiness that dominates the cosmos. Contemplating a void invites reflection on the meaning of emptiness and space. Thinking about these immense regions challenges our intuitive notions of space as merely the absence of objects. Voids highlight that space itself has properties, geometry, and dynamics. Their existence prompts philosophical reflection on the nature of nothingness and its role in structuring reality. They offer a profound meditation on the substance of emptiness. They represent a state of profound cosmic quiet. In voids, the universe seems to hold its breath. Far from the energetic processes within galaxies, the environment is dominated by stillness and cold. The near absence of matter means a near absence of events. They are vast sanctuaries of silence and inactivity, representing the universe in its most passive and undisturbed state. The average density inside a void is about 1 atom per cubic meter. Compared to the air we breathe, containing roughly 10^25 atoms per cubic meter, or even the best laboratory vacuums, the emptiness of a cosmic void is almost absolute. This incredible sparseness means particles travel for millions of years without encountering another particle. It is a realm of profound isolation at the atomic level. This is far emptier than the best vacuum chambers created on Earth. Human technology cannot replicate the degree of emptiness found naturally in cosmic voids. Even our most sophisticated vacuum systems contain vastly more residual particles per unit volume. Voids represent a level of vacuum unattainable through artificial means, a natural state of near-perfect emptiness perfected over cosmic eons. If you were inside a void, you would feel no gravitational pull in any particular direction. Due to the extreme lack of mass and the immense scale, the gravitational field inside a large void is exceptionally uniform. An observer floating freely would experience almost perfect weightlessness with no discernible pull towards any specific structure. It would be a state of serene suspension in a vast, indifferent gravitational landscape. The temperature inside a void is uniformly cold, around 2.7 Kelvin. The only significant source of heat within a deep void is the cosmic microwave background radiation, the faint afterglow of the Big Bang. This ancient light fills all of space with a near-perfect blackbody spectrum corresponding to a temperature just 2.7 degrees above absolute zero. Voids are vast regions bathed in this uniform, primordial, and profoundly cold light. This is the temperature of the faint afterglow of the Big Bang. The CMB represents the residual heat left over from the hot, dense early universe cooled by 13.8 billion years of cosmic expansion. Its near-perfect uniformity across the sky is a cornerstone of modern cosmology. Within voids, far from any local heat sources, the temperature defaults to this fundamental universal background level. They are places where you feel the cool breath of creation itself. Voids are vast regions of thermal equilibrium and peace. Lacking significant internal heat sources or density gradients, the environment within a void is remarkably uniform and stable. It represents a state close to thermodynamic equilibrium, where energy is distributed evenly and processes happen incredibly slowly, if at all. They are immense domains of unchanging, cold tranquility. Voids are not just passive gaps. They actively shape the cosmic web. While formed by the evacuation of matter, voids also exert an influence on the structures around them. Their slightly faster expansion acts like a gentle outward pressure, helping to compress the matter in the surrounding filaments and walls, making these structures appear sharper and more defined. The emptiness actively participates in sculpting the luminous patterns of the universe. The holes in the cosmic sponge help define the shape of its walls. The Boötes Void is famously large and spherical, nicknamed the Great Nothing. Discovered in the early 1980s, this particular void captured the astronomical imagination due to its immense size, nearly 330 million light-years in diameter, and its remarkably spherical shape. Initial surveys found almost no galaxies within this colossal volume, leading to its evocative nickname, while later, more sensitive observations have revealed a sparse population of faint galaxies residing within its borders. It remains one of the most striking examples of large-scale emptiness known in the cosmos, a vast bubble of profound underdensity. It stands as a stark monument to absence on a grand scale. Voids offer a sense of profound scale and perspective. Contemplating the sheer size of a cosmic void forces a recalibration of our sense of place in the universe. Our entire galaxy, vast as it seems to us, would be utterly lost within such an expanse. Even the superclusters, containing thousands of galaxies, appear as mere threads surrounding these dominant empty regions. Voids provide a humbling backdrop, emphasizing the immense scale upon which the cosmos is constructed and the relative rarity of the dense, luminous places we inhabit. They frame the significance of structure against a canvas of immensity. Our bustling galaxy is surrounded by immense quiet. The Milky Way resides within a filament of the cosmic web, a relatively populated area. Yet, even our busy neighborhood is bordered by regions of significantly lower density, including the nearby local void. This reminds us that even centers of activity are ultimately islands within a much larger, predominantly tranquil ocean. The universe's default state appears to be one of sparseness and low activity, making regions like ours exceptional. The ambient condition of the cosmos is stillness. They represent the vast majority of the stage on which the cosmic drama unfolds. While our attention is naturally drawn to the bright stars, colliding galaxies, and exploding supernovae, these events occur within the relatively small confines of the cosmic web's filaments and clusters. The voids occupying most of the universe's volume are the enormous passive arenas surrounding these pockets of activity. They are the grand, silent audience chambers watching the slow play of cosmic evolution unfold in the brighter regions. The stage itself is mostly empty space. Contemplating voids can be a calming and humbling experience. There is a unique form of tranquility in considering these immense regions of near-nothingness. They represent a state of profound simplicity and stillness, a counterpoint to the complexity and motion of our everyday lives. Imagining these vast, cold, dark expanses can help to dissolve anxieties and place personal concerns within a vastly larger, unperturbed context. Their emptiness offers a form of mental spaciousness. They embody stillness on an unimaginable scale. Within a void, change occurs incredibly slowly, if at all. Far from the dynamic environments of galaxies, the few particles present drift almost inertly. There are no stellar winds, no shock waves, no significant gravitational tides. It is a realm where time seems to pass almost without event, representing the closest approximation to absolute stasis achievable in our evolving universe. They are domains of deep, enduring calm. The silence within a void is absolute and eternal. Lacking any substantial medium, sound cannot propagate within a cosmic void. Furthermore, the extreme scarcity of matter means energetic events that might produce sound, like collisions or explosions, are virtually non-existent. The quiet within a void is not merely an absence of noise, but a fundamental property of its state, a perfect, unbroken silence stretching across hundreds of millions of light-years and persisting for billions of years. It is the ultimate expression of cosmic quietude, They are places where nothing much has ever happened or ever will. Since their formation, cosmic voids have largely remained passive spectators in the universe's evolution. Lacking the density needed for significant star formation or galaxy assembly, they have maintained their state of extreme emptiness. While the universe around them evolves, the voids themselves represent regions where cosmic history has largely stood still, preserving a near-primordial state. They are zones of minimal cosmic interaction. This lack of activity is a form of deep cosmic peace. The absence of dramatic events within voids can be viewed not as a lack, but as a presence of tranquility. They are vast sanctuaries free from the energetic processes that characterize denser regions. This profound inactivity represents a stable, enduring state of equilibrium, a baseline against which the dynamism of the rest of the universe can be measured. It is peace on a cosmological scale. Voids remind us that emptiness is a fundamental part of reality's structure. Our perception often focuses on objects and matter, but the cosmic web reveals that space, or near emptiness, is just as crucial in defining the universe's architecture. The voids are not simply gaps. They are integral structural components whose presence shapes the filaments and clusters. Emptiness is not nothing. It is a constituent element of the cosmic whole. The universe is built as much from absence as from presence. The universe needs its quiet spaces just as much as its bright places. The interplay between the dense, luminous structures and the vast, dark voids creates the intricate beauty of the cosmic web. The voids provide the necessary contrast and separation, allowing the filaments and clusters to stand out. This cosmic balance between fullness and emptiness is essential for the universe's overall structure and perhaps even its capacity to host complexity within specific regions. Stillness provides the canvas for activity. Drifting through a void would be the ultimate journey into solitude. Imagine a hypothetical voyage across a large cosmic void. For millions upon millions of years, your view would remain almost entirely unchanged. A near-perfect darkness, punctuated only by the incredibly faint, distant smudges of faraway galaxy walls. There would be no nearby stars, no nebulae, just the profound and unbroken emptiness of intergalactic space. It would be an experience of isolation unmatched anywhere else in the cosmos. The darkness inside a void is pure and undisturbed by nearby starlight. Within a galaxy, the night sky is filled with the light of neighboring stars and the faint glow of the galactic plane. Deep inside a void, however, the darkness would be almost absolute. The nearest significant sources of light would be hundreds of millions of light years away, their combined glow contributing only an imperceptible background illumination. It is the truest, deepest darkness the universe has to offer. Voids are gentle counterpoints to the energy of stars and galaxies. They represent the opposite end of the cosmic spectrum from the intense energy release found in star-forming regions or near active black holes. Voids are places where energy density is at its minimum, where processes unfold with extreme slowness, and where the universe exhibits its most passive and quiescent state. They provide the necessary balance to the universe's more energetic phenomena. They represent the universe in a state of quiet rest. If the filaments and clusters are where the universe is actively working, forming stars, merging galaxies, then the voids are where the universe is simply resting. They are vast domains where the fundamental processes of structure formation have largely ceased, leaving behind a stable, unchanging environment. They embody cosmic relaxation on the grandest scale. The faint gas within a void drifts slowly and peacefully. The extremely low density means that the few atoms present travel for immense distances without colliding. Their motion is governed primarily by the slow, overall expansion of the universe within the void, rather than by chaotic turbulence or strong gravitational pulls. It is a state of near perfectly smooth laminar flow on a cosmic scale, the gentlest possible movement of matter. There are no violent collisions or interactions happening there. The extreme isolation of the few galaxies within voids means that major mergers or disruptive gravitational encounters are virtually non-existent. Unlike their counterparts in dense clusters, these galaxies lead remarkably undisturbed lives, evolving primarily through internal processes rather than external violence. Voids are zones free from cosmic traffic accidents. Voids are zones of cosmic non-interference. They represent regions where the evolution of matter and the few structures present proceeds almost entirely unaffected by external influences. This makes them unique environments for studying primordial conditions and the intrinsic properties of galaxies, isolated from the complex environmental effects found in denser parts of the cosmic web. They offer a view of cosmic nature without nurture. They are the calm backwaters of the great cosmic river. If the filaments of the cosmic web are the main channels where matter flows rapidly towards clusters, then the voids are the vast, still pools and eddies off to the side. The currents here are slow, the activity minimal. They are the tranquil, outlying regions far from the main gravitational thoroughfares of the universe. Imagining the emptiness can quiet the mind. Actively contemplating the vast, silent and eventless nature of a cosmic void can be a powerful meditative tool. Visualizing this profound stillness, this lack of complexity and demand, can help to reduce mental clutter and induce a state of calm. The sheer scale of the emptiness dwarfs everyday concerns, offering a potent dose of perspective and tranquility. Voids demonstrate the power of absence in shaping structure. The cosmic web is defined as much by the empty spaces as by the luminous filaments. The voids are not merely passive gaps. Their presence and expansion actively influence the formation and arrangement of the denser structures. This highlights a fundamental principle. Sometimes, what is not there plays a crucial role in determining the form of what is there. Absence possesses a formative power. What isn't there is as important as what is there. This principle, evident in the structure of voids, applies across many scales. In art, negative space defines form. In music, silence creates rhythm and emphasis. In the cosmos, the vast emptiness of voids provides the necessary contrast and boundary that shapes the intricate beauty of the galactic filaments and clusters. The universe is composed of both presence and absence, intricately interwoven. They are serene reminders of the universe's minimalist beauty. There is a stark, profound elegance in the concept of a cosmic void. It represents structure reduced to its absolute minimum, vast, cold, dark space containing only the faintest whisper of matter and the uniform glow of the Big Bang's afterglow. This ultimate simplicity possesses its own unique and compelling form of cosmic beauty. Less can indeed be more. The concept of a void can feel like a deep, calming breath. Inhaling deeply fills our lungs. Exhaling creates a sense of release and spaciousness. Contemplating a cosmic void can evoke a similar mental sensation, an expansion into vastness, a release from complexity, a connection to profound stillness. It is like the universe itself taking a long, slow, and deeply calming breath. They are vast expanses where the universe is simply allowed to be. Voids are regions largely free from the intense gravitational stresses and energetic processes that drive rapid change elsewhere. They represent the universe in a state of minimal interference, where the fundamental properties of space, time, dark energy, and residual matter exist in their simplest, most undisturbed state. It is existence stripped down to its quiet essentials. The transition from a filament to a void happens over millions of light years. Moving from a relatively dense filament of galaxies into a cosmic void is not like crossing a sharp line. Instead, the density of galaxies gradually diminishes over vast distances. The cosmic web fades out gently into the emptiness, a slow and smooth transition from structure to absence, reflecting the gradual nature of the gravitational sorting process that formed them. The borders are gradients, not cliffs. Voids can contain primordial magnetic fields, incredibly weak but vast. While devoid of significant matter, simulations and some observations suggest that cosmic voids might be permeated by extremely weak, large-scale magnetic fields. These fields could be relics from the very early universe, perhaps generated during the Big Bang or the inflationary epoch. If confirmed, they would represent some of the oldest and most fundamental magnetic structures in the cosmos. Persisting silently in the emptiness, some theories suggest voids might contain exotic forms of dark energy. While the standard cosmological model assumes dark energy is a uniform cosmological constant, some alternative theories propose that dark energy might vary in density or properties. Voids, being regions where dark energy dominates over gravity, are ideal places to search for subtle deviations that could hint at a more complex nature for this mysterious cosmic component. The emptiness might hold clues to the universe's acceleration. Void galaxies tend to have simpler histories than cluster galaxies. Lacking frequent interactions and mergers, galaxies residing in voids often exhibit more regular, undisturbed morphologies like smooth spiral disks, and simpler stellar populations compared to the complex, processed galaxies found in dense clusters. Their relatively uneventful lives preserve a clearer record of their intrinsic formation and evolution. They are case studies in undisturbed galactic development. Studying void galaxies is like studying creatures from isolated islands. Just as island ecosystems often evolve unique species due to isolation, void galaxies provide examples of galactic evolution proceeding without the constant influx of external influences found in denser regions. They reveal how galaxies might develop when left largely to their own devices, governed primarily by internal processes like star formation and feedback. Isolation fosters unique evolutionary paths. The cosmic web structure, including voids, likely influences the spin of galaxies. While seemingly isolated, the large-scale structure surrounding a galaxy imparts subtle gravitational torques over billions of years. Simulations suggest that galaxies forming within or near the boundaries of voids might tend to have their spin axes aligned differently relative to the cosmic web filaments compared to galaxies in denser regions. The quiet emptiness might gently influence the orientation of the luminous structures that eventually form. Even absence can impart a subtle directionality to cosmic motion. Voids challenge galaxy formation, models by hosting surprisingly mature galaxies. While void galaxies are often blue and star-forming, astronomers have occasionally found unexpectedly large, red and quiescent, no longer forming stars, galaxies residing deep within voids. How these galaxies managed to grow so large and cease their star formation so early in such an isolated, gas-poor environment presents a quiet puzzle for theories of galaxy evolution, suggesting that internal processes or rare early mergers might play a stronger role than previously thought. Maturity can arise even in the most isolated of cosmic environments. The study of voids helps constrain the mass of the neutrino. Neutrinos are incredibly light fundamental particles that interact very weakly with matter. However, there are so many of them pervading the universe that their combined mass could subtly affect cosmic structure formation. Because neutrinos move at nearly the speed of light, they tend to smooth out density fluctuations on small scales. By precisely measuring the number and sizes of voids which are sensitive to this smoothing effect, astronomers can place upper limits on the total mass of these elusive particles. The largest empty spaces help weigh the smallest, ghostliest particles. Mini voids exist within the larger filaments and walls. The structure of the universe is hierarchical. Just as superclusters contain clusters and groups, the denser filaments of the cosmic web are not perfectly uniform, but contain smaller regions of lower density within them. These mini-voids are like quiet clearings within the cosmic forest, smaller pockets of relative emptiness embedded within the larger structures. Emptiness exists on multiple nested scales within the cosmic tapestry. The escape velocity from a void is effectively negative. Because a void is an underdense region, the net gravitational pull points outwards. This means that unlike trying to escape a planet or star, an object within a void needs no initial velocity to eventually drift out. The gentle, large-scale gravitational landscape naturally encourages movement away from the void center towards the denser surrounding structures. The path out of emptiness requires no effort, only patience. Voids might contain vast, undiscovered populations of extremely faint dwarf galaxies. Current galaxy surveys are often limited by brightness, meaning we primarily detect the larger, more luminous galaxies. It's possible that cosmic voids are populated by a large number of incredibly small, faint dwarf galaxies that have so far escaped detection. Future, deeper surveys may reveal that the voids are not quite as empty as they currently appear, but are instead filled with these quiet, stellar whispers. The great darkness might hold countless hidden points of faint light. Simulations show voids becoming more spherical over cosmic time, while often irregular, initially due to the complex shape of the surrounding cosmic web. The internal dynamics of voids, driven by dark energy and weak outward flows, tend to make them evolve towards more spherical shapes over billions of years. The process is incredibly slow, but the universe seems to possess a gentle tendency to smooth out and simplify these vast empty regions. Emptiness naturally seeks a state of perfect, simple geometry. The cosmic dipole, the direction the Milky Way is moving relative to the CMB, points away from the local void. Our galaxy's overall motion through space is influenced by all the large-scale structures around us. Part of this motion appears to be a push away from the center of the nearby local void, complementing the pull towards denser structures like the Virgo cluster and the Great Attractor. Our trajectory is shaped by both the presence of mass and the absence of it. We are guided not just by attraction, but also by the gentle pressure of emptiness. Voids are colder in dark matter temperature than filaments. Although dark matter doesn't interact electromagnetically, it does possess kinetic energy, which can be thought of as a form of temperature. Simulations show that the dark matter particles within voids tend to have lower average velocities, a lower velocity dispersion, compared to those in the denser, more dynamically active filaments and clusters. The quiet environment leads to colder dark matter. Even the invisible substance of the cosmos finds a state of deeper chill in the voids. The existence of voids is a key prediction of the standard cosmological model, lambda CDM, the theory that describes our universe based on dark energy, lambda, and cold dark matter, CDM, shaping structure from initial quantum fluctuations, naturally predicts the formation of a cosmic web consisting of dense filaments and vast underdense voids. The observed properties of voids provide strong corroborating evidence for this model, confirming our basic picture of cosmic evolution. The great empty spaces affirm our understanding of the universe's history. Galaxies on the edges of voids might experience gentle tidal forces. While the interior of a void is gravitationally calm, galaxies located near the boundary between a void and a dense filament might feel subtle, large-scale tidal forces. These forces arise from the difference in gravitational pull between the dense structure on one side and the empty region on the other, potentially influencing the galaxy's shape or internal dynamics over long periods. Even proximity to emptiness can exert a subtle, shaping influence. The study of voids is a relatively young field in cosmology. While the existence of voids has been known for decades, the detailed mapping and analysis of their properties has only become possible with the advent of massive galaxy redshift surveys in recent years. Understanding these dominant structures is now a major focus of research, offering unique insights into dark energy, dark matter, and fundamental physics. Charting the great emptiness is a new frontier in cosmic exploration. Voids provide a unique environment to study the faint intergalactic light. Occasionally, stars can be stripped from galaxies during interactions and flung out into the space between galaxies. This creates an incredibly faint, diffuse glow within clusters and potentially along filaments. Voids, lacking bright nearby galaxies, offer the darkest possible backdrop against which astronomers might hope to detect the even fainter starlight that could permeate these vast regions. Emptiness allows the faintest whispers of lost starlight to be potentially heard. The boundary of a void acts like a gentle gravitational repeller relative to the denser regions. While gravity is always attractive, the net effect of a large underdensity is to push objects away from its center towards the surrounding overdensities. This effective repulsion shapes the flow of galaxies and the overall structure of the cosmic web, defining the voids as regions of outward-directed cosmic currents. Emptiness creates a soft pressure, pushing matter towards structure. Voids might play a role in aligning the spins of galaxies over vast distances. Some controversial studies have suggested that the spin axes of galaxies might exhibit subtle alignments with the large-scale structure, potentially influenced by the tidal forces exerted by voids and filaments during their formation. If confirmed, this would imply that these immense, quiet structures can impart a coherent orientation to objects billions of light-years apart. The largest structures might gently comb the rotational patterns of the galaxies within them. Future telescopes will map voids with unprecedented precision. Upcoming large-scale galaxy surveys and next-generation radio telescopes will chart the positions and motions of millions more galaxies, allowing for the creation of far more detailed maps of the cosmic web, including the precise shapes, sizes, and internal structures of voids. This will provide crucial data for testing cosmological models and understanding the interplay of gravity and dark energy. We are poised to create even clearer charts of the universe's empty oceans. The quietest regions may hold the key to the universe's loudest questions. By studying the subtle properties of cosmic voids, their expansion rate, their lensing effects, the properties of the galaxies within them, cosmologists hope to answer fundamental questions about the nature of dark energy, the mass of neutrinos and potential deviations from general relativity. The simplest environments offer the cleanest tests of fundamental physics. Profound answers may lie hidden within the most serene spaces. The gas in voids is thought to contain most of the universe's normal, baryonic matter. Counterintuitively, while galaxies contain the brightest matter, the vast volume of the voids means that the extremely tenuous gas within them likely accounts for the majority of all the protons, neutrons, and electrons in the universe. Most of the ordinary stuff of the cosmos resides not in stars or galaxies, but spread thinly throughout these great empty spaces. The emptiness holds the majority of the substance. Webb telescope might eventually detect this faint intergalactic gas directly. While currently detected primarily through absorption lines in quasar spectra, future observations with highly sensitive instruments like the James Webb Space Telescope might be able to directly detect the faint emission from this warm, hot, intergalactic medium, particularly where it might be slightly denser along faint filaments within voids. This would provide a new window onto this vast, hidden reservoir of cosmic matter. Direct observation could illuminate the tenuous gas. Voids are not entirely static. They have slow internal flows. Although dominated by the overall cosmic expansion, the residual matter within voids is not perfectly stationary. Faint gravitational influences can create very slow, large-scale drifts or flows within the void, often directed outwards towards the surrounding denser filaments. These internal motions are subtle, but contribute to the ongoing slow evolution of the void structure. Even the emptiness has gentle currents. Matter inside a void is expanding away from its center. Because the void is an underdense region, the net gravitational pull on any matter inside it points outwards, towards the denser surrounding structures. Combined with the slightly faster local expansion of space, this results in a gentle but persistent outflow of material away from the void's center. Voids actively, albeit slowly, evacuate themselves over cosmic time. Mapping the shapes of voids can test theories of gravity on large scales. General relativity makes specific predictions about how structures like voids should grow and evolve. By precisely measuring the shapes, sizes, and distribution of voids in large galaxy surveys, cosmologists can test whether gravity behaves as expected on these immense scales, or if alternative theories might be needed to explain subtle deviations. The geometry of emptiness probes the laws of attraction. Deviations from expected shapes could hint at new physics. If voids are observed to be, for example, more spherical or expanding faster than predicted by standard models incorporating general relativity and dark energy, it could be evidence for modifications to gravity on cosmic scales or a more complex behavior of dark energy. The precise form of the cosmic emptiness holds clues to the fundamental forces shaping it. The local void is a large nearby void that our local group is moving away from. Our own collection of galaxies, including the Milky Way and Andromeda, lies near the edge of a significant underdensity known as the local void. Our observed motion through space includes a component directed away from the center of this void, suggesting its lower gravity, or effective repulsive force due to surrounding structures and expansion, influences our cosmic trajectory. We are being gently nudged away from our neighboring emptiness. Voids can affect the paths of light rays more than expected, a lensing anomaly. Some studies have suggested that light traveling through voids might experience slightly stronger gravitational lensing effects, both weak demagnification and subtle path bending, than predicted by models based solely on their low matter density. This is another area where voids serve as laboratories to test our understanding of gravity and potentially the nature of dark energy, which also influences space-time curvature. The passage through emptiness might be subtly complex. Cosmic voids represent the ultimate state of low density. They are the natural endpoint for regions of the universe that began with slightly less matter than average. Gravitational evolution inexorably drives these regions towards ever greater sparseness. They embody the concept of dilution on a cosmic scale, representing the maximum achievable emptiness within the framework of cosmic structure formation. They are places where entropy has almost reached its maximum. Entropy, or disorder, tends to increase over time. Voids, being vast regions of diffuse, cold, and uniform gas, represent a state very close to maximum entropy or thermal equilibrium. Lacking significant gradients or structures, there is little potential for further spontaneous evolution or complex processes to occur within them. They are domains approaching a final state of cosmic equilibrium. They offer a glimpse into the potential far future state of the universe. If the universe continues to expand under the influence of dark energy, the far future will likely resemble a vastly scaled-up version of a cosmic void. All structures not gravitationally bound will recede from each other, leaving behind isolated islands, like our merged local group, in an immense, cold, dark, and increasingly empty expanse. Voids preview the universe's ultimate state of quiet isolation. The minimal structure within voids makes them laboratories, because they lack the complex interplay of galaxy mergers, star formation bursts, and active black hole feedback found in denser regions. Voids provide a cleaner environment to study certain fundamental processes. For example, the properties of the faint intergalactic gas or the behavior of dark energy might be measured more clearly against the simple backdrop of a void. Simplicity allows for clearer measurements of fundamental properties. They allow us to study the faint traces of the universe's initial conditions. The slight density variations and subtle flows within voids are direct relics of the primordial fluctuations present shortly after the Big Bang. Because relatively little has happened within voids since then, they preserve a less processed record of these initial conditions compared to the highly evolved structures in clusters and filaments. Emptiness acts as a form of cosmic fossil record. Voids are the quiet backdrop against which the story of structure unfolds. The luminous narrative of galaxy formation, stellar evolution, and cosmic collisions plays out primarily within the filaments and clusters of the cosmic web. The voids serve as the vast, silent, and essential context for this story, the dark stage upon which the brighter actors perform their slow, cosmic dance. Their presence gives meaning and definition to the structures we observe. The universe is mostly made of quiet emptiness. This is perhaps the most profound takeaway from the study of large-scale structure. Our intuitive focus on objects and light belies the reality that the overwhelming majority of the universe's volume consists of these vast, dark, cold, and nearly empty voids. Recognizing this shifts our perspective, highlighting the preciousness of complexity and the fundamental nature of stillness in the cosmos. Emptiness is the dominant cosmic geography. This emptiness is not nothingness, but a fundamental part of the whole. Voids are not mere gaps. They are integral components of the cosmic web's structure and dynamics. They possess physical properties, residual gas, dark energy, weak magnetic fields, influence the evolution of surrounding structures, and affect the passage of light. Understanding the universe requires understanding its empty spaces as much as its full ones. Absence is a constituent element. Voids are places of profound stillness and stability. Their extremely low density and weak gravity mean that processes within them unfold incredibly slowly. They represent regions where the universe has reached a state of deep equilibrium, largely insulated from the more dynamic events occurring elsewhere. They embody persistence and tranquility on the largest scales. They invite a sense of calm and release. Contemplating the immense, uncluttered expanse of a cosmic void can have a soothing effect. It offers a mental escape from density, complexity, and noise. Imagining this profound stillness can foster a feeling of inner spaciousness and peace. Their vacancy offers a respite for the mind. Thinking about voids helps dissolve feelings of being crowded or rushed. In a world that often feels overwhelmingly busy and dense, the cosmic perspective offered by voids provides a powerful antidote. It reminds us of the vast backdrop of silence and stillness against which our lives unfold, potentially lessening feelings of pressure and urgency. They offer a cosmic context for finding inner calm. They represent the universe taking a long, deep, quiet pause. If the formation of stars and galaxies is the universe inhaling and concentrating matter, then the voids are like the long, slow exhalation, the release into vastness and sparseness. They embody a state of cosmic relaxation, a pause in the dynamic processes of structure formation persisting across billions of years. Voids represent the ultimate triumph of expansion over gravity. On smaller scales, gravity wins, forming stars, galaxies, and clusters. But on the largest scales, represented by the voids, the initial slight underdensity combined with the accelerating expansion of the universe ensures that gravity can never pull these regions back together. Voids are monuments to the ultimate power of cosmic expansion. They are domains where the universe's outward breath prevails. They are vast reservoirs of near-pristine primordial gas. The gas within voids has undergone very little processing through stars compared to the gas inside galaxies. It therefore retains a chemical composition much closer to the original mixture of hydrogen and helium created in the Big Bang. Studying this gas provides a direct window onto the raw material from which the first structures were formed. Emptiness preserves the universe's original chemical signature. The cosmic web structure, including voids, likely formed within the first billion years. While voids have grown larger since then, the basic pattern of filaments and empty spaces was likely established very early in the universe's history, guided by the initial distribution of dark matter. The quiet architecture we see today has ancient foundations. The blueprint for emptiness was drawn shortly after the dawn of time. Voids are not truly empty of photons. They are filled with the ubiquitous cosmic microwave background radiation, the faint light from the Big Bang. They are also traversed by photons from distant galaxies and quasars, as well as potentially a background of primordial neutrinos. While lacking significant matter, they are permeated by these various forms of radiation. Emptiness is bathed in the faint, residual light and particles of the cosmos. The concept helps us appreciate the scale difference between emptiness and nothingness. While profoundly empty compared to our surroundings, cosmic voids are still part of the physical universe, filled with space, time, physical laws, faint gas, and background radiation. They represent an extreme low-density state within reality, distinct from the philosophical concept of absolute nothingness. Cosmic emptiness is a physical state, not a metaphysical void. Their existence was first strongly suggested by pencil beam galaxy surveys. In the 1980s, astronomers conducted surveys that looked deep into space along narrow lines of sight. They found that galaxies were clustered at certain distances, separated by vast regions with almost no galaxies. This provided the first compelling observational evidence for the existence of large-scale voids, confirming earlier theoretical ideas. Staring deeply into narrow cosmic corridors revealed the great empty rooms between them. Voids are the ultimate expression of cosmic structure growing via gravitational instability. The standard model explains structure formation as gravity amplifying tiny initial density fluctuations. Voids represent the extreme outcome of this process for underdense regions. Gravity actively removes matter, making them emptier and emptier over time. They are the inverse of galaxy clusters, sculpted by the same fundamental force. Gravity builds structures by digging holes elsewhere. Contemplating a void can evoke a feeling of serene detachment. Imagining the perspective from within a vast cosmic void, the immense distances, the profound silence, the lack of nearby events, can foster a sense of detachment from immediate concerns. It provides a mental space of quiet indifference, a reminder of the vast, unperturbed backdrop against which all cosmic activity occurs. Emptiness offers a perspective of profound neutrality. The universe's structure is hierarchical, with voids existing on multiple scales. Just as matter clumps into stars, galaxies, groups, clusters, and superclusters, emptiness also seems to have a hierarchy. There are the dominant large voids between superclusters, smaller voids within filaments, and potentially even tinier voids within individual galaxy groups. The pattern of emptiness repeats itself on smaller and smaller scales, mirroring the structure of matter. Absence, like presence, builds upon itself in nested layers. Voids are fundamentally cold, both physically and dynamically. Their temperature is near absolute zero, and their gravitational potential is shallow, meaning particles within them have low kinetic energy, cold in a dynamic sense. They lack the energetic processes that heat gas in clusters or accelerate particles. Voids represent the universe in its most chilled and quiescent state. They are regions of deep cosmic refrigeration and stillness. The study of void shapes can reveal subtle alignments in the cosmic web. Analyzing the orientations and shapes of voids and how they connect to the surrounding filaments provides information about the stresses and flows that shape the large-scale structure. Voids are not just passive bubbles. Their geometry encodes details about the history of cosmic expansion and gravitational collapse. The contours of emptiness trace the history of cosmic forces. If dark energy changes over time, the evolution of voids would be affected. The rate at which voids grow and merge is sensitive to the properties of dark energy. If dark energy is not a constant but changes its strength over cosmic history, this would leave a subtle imprint on the statistical properties of the void population. Voids thus serve as potential probes for the dynamical nature of the universe's acceleration. The growth rate of emptiness could reveal the secrets of cosmic acceleration. Voids represent the ultimate outcome of regions that lost the initial cosmic tug-of-war. In the early universe, regions competed gravitationally. Those with slightly more matter attracted more, eventually forming structures. Those with slightly less matter lost out, progressively giving up their material to their denser neighbors and evolving into the voids we see today. They are the quiet evidence of gravity's discriminating power. Emptiness is the gentle consequence of losing the initial gravitational lottery. The transition zone between a void and a filament is a unique environment. Galaxies located on the outskirts of voids, where they begin to feel the stronger gravitational pull of a nearby filament, might experience gentle gas flows or subtle tidal forces that influence their evolution. This interface region is a quiet frontier, marking the boundary between profound emptiness and emerging structure. The shoreline between the empty ocean and the populated land fosters unique conditions. Voids contain a fossil record of the universe's expansion history. Because their growth is sensitive to the cosmic expansion rate at different epochs, the statistical distribution of void sizes and shapes observed today carries imprinted information about how the universe's expansion has changed over time. Decoding this information provides another way to reconstruct cosmic history and study dark energy. The dimensions of emptiness serve as a cosmic chronometer. The near absence of feedback processes makes void physics simpler. Unlike galaxies and clusters, where complex feedback from supernovae and active black holes significantly affects the environment, voids are largely free from these processes. This makes their evolution relatively simpler to model and understand, governed primarily by gravity and cosmic expansion. Their simplicity makes them clean theoretical testbeds. Emptiness offers a laboratory largely free from complicating factors. Voids highlight the immense scale of homogeneity in the universe. While structured into webs and voids, the universe, on the very largest scales, larger than the biggest voids, appears statistically uniform or homogeneous. Voids represent the largest deviations from this average state, defining the upper limit of significant cosmic structure. Beyond their scale, the universe settles into a grand, quiet uniformity. They mark the transition from cosmic structure back to cosmic smoothness. The concept of a void challenges our intuitive bias towards things. We tend to focus on objects and structures, often overlooking the spaces between them. Cosmic voids force us to acknowledge the importance and prevalence of emptiness in the universe's structure and evolution. They teach us that absence can be as significant and informative as presence. Understanding the universe requires appreciating its empty spaces. They are vast regions where cosmic potential remains largely unrealized. Voids contain primordial gas that has never been incorporated into stars or galaxies. They represent enormous reservoirs of raw material that, due to low density, never underwent the gravitational collapse necessary to form luminous structures. They are quiet landscapes of what might have been if the initial conditions had been slightly different. Emptiness holds the universe's unexpressed possibilities. The few atoms within a void participate in the universe's overall expansion. Each particle residing within a void is carried along by the stretching fabric of space-time. Their distances from each other increase over time simply due to the expansion of the space they occupy. They are passive tracers of the universe's fundamental dynamic behavior, gently receding from everything else. Even the loneliest particles partake in the cosmic outflow. Voids are the ultimate expression of gravitational segregation. Over cosmic time, gravity has effectively sorted the universe's matter, concentrating it into dense structures and leaving behind these vast regions of profound emptiness. Voids represent the completion of this sorting process on the largest scales, the final state of regions destined to remain underdense. Gravity's patient sifting created both the piles and the empty spaces between. Their immense volume means even rare events might occur within them over eon. While extremely sparse, the sheer size of voids means that statistically, even highly improbable events like the random formation of complex molecules, or perhaps even isolated star formation from primordial gas clouds, might occur somewhere within their vastness over the immense timescales of the future. Universe vastness allows room for even the most improbable quiet occurrences. Voids represent a cosmic baseline, a reference point of minimal activity. By comparing processes occurring in dense environments to the near absence of those processes in voids, astronomers can isolate the effects of environment on galaxy evolution and other phenomena. Voids serve as the ultimate control group in the grand experiment of cosmic structure. Formation.emptiness provides the essential benchmark for measuring cosmic influence. Contemplating cosmic voids connects us to the profound silence of existence. Beyond the noise of our world and the light of our galaxy lies this dominant state of deep, undisturbed quiet. Imagining these vast, silent expanses can evoke a sense of peace and connection to the fundamental stillness that underlies the more active parts of the cosmos. In their silence, we can perhaps hear the universe's fundamental note. They are vast, dark canvases upon which the faint light of distant structures is painted. The emptiness of voids provides the necessary contrast for the luminous filaments and clusters of the cosmic web to be visible. Like black velvet displaying scattered jewels, the voids allow the structure of the universe to be seen in all its intricate beauty. Darkness is required to appreciate the faint patterns of cosmic light. Voids are regions where space-time itself is the dominant feature. Lacking significant matter content, the dynamics within voids are primarily governed by the intrinsic properties of space-time, its expansion, and the influence of dark energy. They are places where we can study the behavior of the cosmic fabric itself, relatively unperturbed by the presence of matter. Emptiness allows us to observe the stage without the actors. Their existence is a gentle affirmation of our cosmological models. The fact that our best theories of the universe based on gravity, dark matter, and dark energy acting on initial quantum fluctuations naturally predict the existence and properties of cosmic voids is a major triumph. These vast empty spaces are not anomalies, but expected features, confirming the basic correctness of our understanding of cosmic history. The predicted emptiness matches the observed quietude. Voids embody the universe's tendency towards simplicity on the largest scales. While complexity arises in dense regions, the dominant volume of the universe settles into this state of extreme simplicity. Cold, dark, sparse, and uniform, voids represent a kind of cosmic default state, the baseline condition from which localized complexity emerges. The grandest structures resolve into the simplest state. They are vast domains of undisturbed primordial history. Because so little processing of matter has occurred within them, voids preserve a relatively clean record of the conditions of the early universe. The gas within them retains its near-primordial composition, and the subtle density fluctuations trace the initial seeds from the Big Bang with minimal alteration. They are quiet archives of cosmic beginnings. Emptiness holds the clearest memory of the universe's birth. The few galaxies inside evolve in a state of peaceful non-interaction. Void galaxies are spared the gravitational harassment, gas stripping, and frequent mergers that characterize life in denser environments. They drift through their immense surroundings largely undisturbed, their evolution proceeding at a slower, more internally driven pace. They are exemplars of serene galactic aging. Isolation fosters a long and undisturbed existence. Voids are the ultimate cosmic deserts, yet even deserts possess a subtle ecosystem. While seemingly barren, voids contain faint gas, perhaps weak magnetic fields, and maybe populations of undetected dwarf galaxies. They represent an extreme low-energy ecosystem governed by subtle physics and evolving on immense timescales. Even the emptiest places possess a quiet, minimal form of existence, life, or at least structure. persists even in the sparsest environments. Contemplating their scale provides a profound sense of temporal perspective. The time it takes light to cross a void dwarfs human history. The processes shaping them unfold over billions of years. Thinking about voids anchors our perception in the deep time of the cosmos, making our own moments feel simultaneously fleeting and connected to an immense, enduring reality. Emptiness teaches the vastness of cosmic duration. A cosmic void is a place of perfect, undisturbed, and gentle rest. It is the universe in its most passive state, a realm of profound silence, stillness, cold, and darkness, persisting across unimaginable scales of space and time. It is the ultimate embodiment of cosmic peace, the serene background against which all the light and motion of the universe unfolds. It is the universe, quietly and deeply asleep. And so our exploration of the vast, quiet spaces of the cosmic voids draws to its peaceful close. We have journeyed through the largest structures in the universe, finding not objects, but profound absences, regions of deep stillness that define the luminous patterns of the cosmos. The idea of these immense regions defined by their quiet absence can now gently recede, leaving behind a feeling of deep calm and spaciousness within you. It is time to let it all go. We have floated through realms where galaxies are rare islands and silence is absolute. We have considered how these voids were sculpted by gravity and how they reveal the subtle push of dark energy. We have found a strange, minimalist beauty in their profound emptiness, recognizing that these quiet spaces are essential components of the cosmic whole. Let the feeling of this immense quiet pervade your own sense of being, bringing a deep sense of peace. The same dark energy that gently expands the voids permeates the space you inhabit. The same fundamental laws that sculpt these structures govern your own quiet rest. You are part of a universe that finds structure as much in absence as in presence, a cosmos where stillness and silence dominate the grandest scales. Find comfort in this connection to the vast, serene background of existence. You are held within this immense and peaceful reality. And now, as you allow yourself to sink deeper into relaxation, let go entirely of thoughts about the cosmos. Allow your mind to become as empty, still, and serene as a great cosmic void itself. There is nothing left to explore, nothing left to hold on to. Your only purpose now is rest. Surrender to the quiet darkness, to the gentle embrace of sleep, and allow yourself to drift into a state of perfect, undisturbed tranquility. May your rest be as deep and vast as the quietest corners of the universe. Good night.